Hey everybody, Zachariah J here again with some Calc 3B. Going to start working on Chapter 6. Hope you enjoy the video. One of the things that I remind everyone at the beginning of these videos is I am not an instructor. I'm taking the course just like many other students at this time that I'm making the video. So if I make small mistakes or whatever, I'd encourage you to put them into the comment section and I will respond back to you. Other than that, let's see what we can do with Chapter 6. Alright, let's jump right into Section 6.1, Areas Between Curves. And our first question is, find the area of the region bounded by the curves y equals e to the x and y equals e to x between 0 and 1. So e to the x passes through y equals 1, so we'll write that here. And e to the 2x also passes through y equals 1, except it's just a steeper curve. So I'll do that in green here. And doink, do my best to get this somewhat close. Now I'm going to make it not scaled in the x direction, otherwise we'll just have this tiny little spot for our area. So I'm just going to move the x equals 1 to be way out over here so we can see this funny looking triangular shape. There you go. So our area is this area right here. So we want to find out what the the area of this area is, or this region. So we'll define our region as from 0 to 1, which is given to us in the problem, so we don't need to do any sort of math work to find out what it's between. We can just see it right there. And then we need to look at the top of our area, and this is x equals 0, and this is x equals 1. That's where I got those. So we need to look at the top of our region and our bottom of our region. So we're going to go from the smaller number to the bigger number. So e to the x is the bottom. It's less than or equal to y. And then the bigger number, oops, this is supposed to be an x, e to the 2x. So this is basically, we put the bottom first and then the top at the end as they are getting greater as you move to the right. So the formula we use is the area is equal to the integral between a and b of our f of x minus g of x. And then that is, of course, dx. Now, what is f of x and g of x in this problem? Well, really we can think of these as top minus bottom. So we got our top here and our bottom here. So whatever the top part is going to be our f of x for this example, and our bottom is going to be g of x, or the other function, right? So now that we've defined our function, or our region, it's easy for us to just write our integral from 0 to 1, and I'm getting those numbers from here and here. And then again, we're doing top minus bottom, so this function is my top, so I'm going to write that first, e to the 2x, and minus our bottom, and this one right here is my bottom of the function, and that is e to the x, and then this of course is dx. So now if we take the function, or take the integral rather, we are going to end up with 1/2 e to the 2x minus e to the x. The integral for e to the x is just e to the x, evaluated from 0 to 1. Now, of course, if we put in 1/2 e to the x times 1, we just hit e squared minus e to the first power, which would just be e, and then minus, it's going to be, I'll put brackets so we can see what's going on here. We're going to have minus 1/2 e to the 0. Now this is important to put this down because e to the 0 is actually a different number. It's not 0. So we have 1/2 e to the 0 minus e to the 0. And as we should remember, e to the 0 is equal to 1. So we'll bring this down. I'm going to have to distribute that negative. And so we've got 1/2 e squared minus e And then we're going to have 1/2 e to the 0. Got kind of a dead spot in my iPad here. Anyway, e to the 0 is equal to 1, so if we put the that's just going to be 1/2, and then minus 1 for that section. So we'll combine everything we can here. 1/2 e squared minus e, and then combining that plus 1. Wait a minute. I think I have made a mistake in distributing my negative sign here. So, yes, I have. Let's erase the plus sign here. Think. Alright. That should be minus 1/2 and plus 1. And if you have negative 1/2 plus 1, that gives you plus 1. Or, sorry, plus 1/2. And there you go. There's the answer. So in 6.2, we have a couple things that we have to go over. First one is area by cross-section. So find the volume of the solid whose base is the region defined, or region between the parabola y equals 4 minus x squared and the y-axis, and whose vertical cross-sections are perpendicular to the y-axis are squares. Alright, so there we go. Let's draw this parabola. It would intersect the y equals 4, and it's a parabola opening down. Now, the first thing we need to do is find where this crosses the x-axis here. Oops, sorry about that. So the sections are perpendicular to the y-axis. So that means we're dealing with a slice, rather, that goes through this parabola, or this solid, here. So, I mean, if I drew this in a 3D kind of way, basically here is the bottom, and it asks for squares, so you can see this is going to be a square, and here's x times x. That would give us the area of this, so x squared is the area. And then no matter where we took this slice through here, we just keep getting boxes. And the boxes would be getting smaller and smaller, smaller, smaller as we got up, because we have a parabola, so it's moving in. So anyway, oops, sorry about that. Our area is basically x squared, and this is our x here. So we need to know what x is. Well, it's part of this function. So let's start with the bottom points here, and we'll find out where they are. Y equals 4 minus x squared. Well, that is going to equal x equals plus or minus root 4 minus y. So you just algebraically move this expression around, so we have this in terms of y. So we want to make sure that we are following the instructions, where we have the cross sections going perpendicular to the y-axis. So now we know there's points here and here. We're going from this point to this point. So x can be kind of considered as, well, not kind of, it is considered as 2 times the root of 4 minus y. Because there's this axis of symmetry here, so we have 2 times that. So our volume, or area rather, is 2 root 4 minus y, and that's squared because we said earlier it's x squared. So we found out what x is, so now we know what that is. So we can pull this 2 squared is 4, so we can pull that out. And then we can cancel out this root sign, and then we end up with 2 minus y. Yeah. No. it's 4 minus y. The root sign cancels with this squared part, and so we end up with 4 minus y. There we go. So our region actually is going from 0 to 4, and we get the 4 from basically right here. So that's the top of our parabola, since we're going from the x-axis to there. There you have it. Now our formula is volume is equal to the integral from a to b, and since we're doing squares, it's x squared dx. Now if you were doing circles, it would be pi r squared, or pi r, whatever the area of a circle is. So you'd insert that there. You have to figure out that part. So anyway, our volume is the integral from 0 to 4, because we found that here and here. Here is our r, and I already squared it, so I'm just going to put in what I squared, which was 4 times quantity 4 minus y, and it's dy, because we're working with y here. Next step, I can pull this 4 out, or I could distribute it. To me, I think it would just be easier to pull the 4 out, so I'm just going to rewrite this as 4, and then the integral 0 to 4, and then 4 minus y dy. Now, if I take this integral, I'm going to have 4 times 4y and minus 1/2 y squared, evaluated from 0 to 4. And then, of course, now we're just going to plug in these numbers into our antiderivative here. Hang on a second. Yeah. All right, here we go. Let's put it up here so we have a little bit more room. 4 times the quantity 4, and then we'll plug in our 4 for y, and then minus 1/2 4 squared. And then plugging in 0 would just get us 0 for the rest of that. So this is all we really need. So 4 times the quantity, and then 4 times 4 is 16. And then 1/2 4 squared. So that's minus 1/2 4 squared. That 4 squared is 16 divided by 2. That's 8. So there you go. And then 16 minus 8 is going to be 8 again. So 4 times 8, that's going to be... So that was area by cross-section. And now we're going to do area of the volume by disk method. So a volume that's rotated about an axis, as you can see by this problem. Now we have y, x to the negative 2. We can rewrite this as y over x squared. Now it should be something that's more readily recognizable. And then we have these other boundaries. And this tells us that we're going to be in quadrant 1. So that's why I've only drawn a graph for quadrant 1. And we are going to be rotating about the x-axis. So 1 over x squared is just like this. It's just slightly different concavity than 1 over x. The y equals 0 is going to be this line, of course. And then x equals 1. Let's do that in green. We'll put that here. And really, I should be labeling these. So let me go back and label these really quick. So this is x equals 1. This was y equals 0. And this curve is y equals 1 over x squared. And get one other color. I guess I'll use light blue. And that's going to be x equals 4. We'll put that right here. Again, this might not be perfectly to scale, but it gives us a rough sketch of where our area is. Now, notice we cannot do like washer method because we've got these 2 different boundaries if we would go perpendicular to the y-axis. But it tells us we're going against the x-axis, or rotating around the x-axis anyway. But just wanted to make sure you can see, if you wanted to find a volume, you use the correct method. Anyway, so we're rotating around the x-axis here. So we have to use a radius that is perpendicular to the axis of rotation if we're going to use the disk method. And the axis of rotation needs to be a boundary of the area, which we have here. So we have the area is going to be equal to the integral from a to b of pi r squared dx, or I mean, I guess it could be dy as well if we are working with y, just as a side note. But notice we're working with x here, so working with x, so the dy is going to be out, so it's definitely going to be dx. Anyway, we have pretty much everything we need to set this up here. So let's use green, I guess. The area is going to be equal to, and I'm going to pull the pi out, and the integral from 1 to 4, we're given those in the problem anyway, but we graphically drew it. And then it's going to be, I'll just write the radius here is 1 over x squared, or we could say x to the negative 2, right? Which was actually what was given to us in the beginning of the problem. Now, we're going to have to square that. I'll just put x to the negative 2 squared, and then it's dx, which matches our formula. Now we're going to square our x to the negative 2, and that's going to give us x to the negative 4, which, if we take that integral, we put that down on the bottom, so it would be 1 over x squared. Well, actually, we'd make this 1/3 x to the negative 3, right? Yes. So we'd add 1. Yep. This would be a negative 1/3 x to the negative 3, evaluated from 1 to 4. Now, we can pull that 1/3 out, so we can just put negative pi over 3, and then on the inside we end up back with, well, 1 over x to the 3rd, which makes this easier to plug in the 1 and the 4. Oops, not 3. I'm 3 happy. Anyway, 1 to 4. So pi over 3, negative, and 1 over 4 to the 3rd, minus 1 over 1 to the 3rd. And then that's going to work out to be, the 4 cubed is 64, so we got negative pi over 3 times the quantity 1 over 64, and then 1 over 1, or 64 over 64, so we can find common denominators here. And then we're running out of room, so I'm going to move up here. So we got negative pi over 3 times the quantity negative 63 over 64, which, you know, if we multiplied this across, this would be positive. It would be pi over 63, pi over 3. I'm going to leave the 3 out just so you can see this. It'll make it easier. Oops. Hang on a second. Let's undo that and put the parenthesis down here. It's 3 times 64. This 3 can reduce with this guy, so we got pi, and this negative's not supposed to be here. Anyway, 21 pi over 64. So that's going to be our final answer for this guy, and that is the disk method. Last concept for 6.2 is the washer method. And in this example, we have the solid that's defined by y equals x squared plus 2 and y equals 10 minus x squared about the x-axis. So y equals x squared plus 2 is parabola opening up, crossing the positive 2 on the y-axis, and then 10 minus x squared is parabola opening down, crossing the positive 10 point on the y-axis. So we need to figure out what these cross points are, so we can figure out the range of our domain here, so we can figure out our integral. So we just set them equal to each other, and as you can see, we end up with x squared equals 4, and then x is equal to plus or minus 2. So this is negative 2, and this is positive 2. Pretty simple on that part of it. So our area in a washer method is the integral a to b pi times r squared, the big R, the big radius, minus the small radius squared, and it could be dx or dy. But as you can see, we're working with x again, so we will be doing with dx in this. So we have to figure out what our big R is and what our little r is. So our big R goes from the x-axis, or the y-axis, x-axis, sorry, all the way up to the top part. So, and we know that's 10 minus x squared. And our small r goes from the same point up to the bottom part of our region, and that's x squared plus 2. So really, we just need to plug all of this information into our integral. So we have the area is equal to the integral negative 2 to 2 pi, and our big R, which was 10 minus x squared, and then we have to square that, minus our small r, which was this guy, which is x squared plus 2. So let's put that in, x squared plus 2, and that's squared, and then of course close this bracket, and then we got dx. Now to do this, we need to FOIL both of these guys. So off to the side, I'm just gonna FOIL them out for you. Do them really quick here. And x squared minus 10, I'm sorry, 10 minus x squared, and so 10 times 10 is 100, and this is going to end up being 20x, and then plus x to the fourth. There we go. So that's going to be the first one, and then of course we've got to FOIL the second one. Let's just put the first part in. I'm pulling the pi out, the integral negative 2 to 2. And what was the first? It's 100 minus 20x squared plus x to the fourth. Okay, so we're going to have minus and then whatever the second one is FOILed out to. So let's go ahead and FOIL this one, x squared plus 2. And x squared plus 2. So that's going to be x squared plus, x to the fourth plus x to the fourth plus 4x squared plus 4. 2 times 2 is 4, yeah. So that's what's going to go in the parentheses down here. So we'll transfer all of this into here. And there we go. Now remember dx at the end. And we're going to have to distribute that negative. So actually let's just bring all of this down here. Little side work underneath here. 100 20x plus x to the fourth minus 4x squared minus 4. 4x squared minus 4. Yeah, there we go. I didn't miss anything. So we combine the 100 and the minus 4, we get 96. We combine the negative 20 and the negative 4x squared, we get minus 24x squared, and these two cancel each other out. So really, what looked like could be terrible turned out to be a pretty short integral. So there you go. We only have to differentiate these two values. So 96x minus 8x to the third, evaluated from, I'm going to make these brackets negative 2 to 2, put the bracket over here and put the pi out here, so we got it all together. All right, now it's time to just sub our values in, and in retrospect we could have used the extra subsymmetry and did 2 times all of this, but we did it with bigger numbers here, so put it over here. Pi 96, and that's times 2 minus 8 times, oops, not x, times 2 to the third minus, open another bracket here, and that's going to be 96 times the negative 2 and minus 8 times negative 2 to the third. Close all that up, and now we'll simplify all of this, which looks like a mess, but we got pi 96 times 2, I get 192, and this is going to be minus 64, and then this is going to end up being a plus 192, and then a minus 64. So then we simplify this, and let's just combine the two 192s together. Oh, by the way, yeah, I distributed this negative. We got 2 times 2 is 4, times 2 is 8. That's going to be negative 8. Negative 8 times negative 8 is positive 64, and then distributing that negative, that's how we got a negative 64 in the lower. Anyway, so let's combine these two 192s to 384 and the two 64s to be minus 128. Pi out front. There we go. And now if we simplify this a little bit further, we will find that we have 256 pi, or pi 256 is what I get. Yep. All right. There you go. That's the Washa method.
Okay, so now we move on to 6.3 cylindrical shells. And we find the volume of the solid generated by revolving the region bounded by 5 over x squared, which looks like this. And x equals 1, which we'll put 1 right here. X equals 2, we'll put it right over here. Now, as I said before, actually I'll label these. This doesn't necessarily need to be exactly to scale. It just needs to give us a general idea of what our region looks like. So here's x equals 2. And then, of course, we have this section, which is y equals 0. So now we see that we can't necessarily use the washer method because here we have two different bounds for what we'd use for a washer method. I mean, actually, since we're rotating about actually we are rotating about the y-axis. So we couldn't do the washer method because of these two different bounds here. So what we're going to have to do is use the cylindrical shell method. And how we do that is this right here will be defined as our radius. And we'll put that here as, well, our radius is going to be 5 over x squared, because every point on the upper part is going to be 5x squared. This part is going to be defined as our height, and our height in this case is going to be just the x value. So we are going from 1 to 2. So 1 is less than or equal to x less than or equal to 2, and I got those numbers from here and here. And our formula for cylindrical shells is the volume, V, there we go, is equal to, actually, as the integral from a to b, 2 pi RH. And then this is going to be dx in our case because we are working with x. So I can pull that 2 pi out because that's just a constant. And I'm doing an integral from 1 to 2 as we had before, or we got from here and here. And then we have 5x squared as our radius, and our height was x. And this, of course, is going to be dx. Now the x actually goes up on top, so it's 5x. And that means it's something that we can pull the 5 out and actually make this 10 pi. And one of the x's on the top will cancel with 1 on the bottom, so we end up with 1x, or 1 over x dx. Now this is a formula we should know, so 10 pi, and we take this integral and we get ln of x, and then we evaluate that from 1 to 2. And this is pretty easy. We remember that ln of 1 is equal to 0, so we don't have to worry about the 1. So we'll just do 10 pi times ln of 2. And without a calculator, we really can't reduce this any further, but there you go. And we know 2 is positive.
So this next section, 6.4, is about work, which you could say I've been doing work all this time, and I wouldn't argue. But these are work problems. The force needed to stretch a spring x meters from its natural length is a function. F of x equals 18. I'm just going to put that over here. How much work is done by stretching the spring 60 centimeters? So that's the length that I want to stretch this thing, 60 centimeters. Now, I like to work in meters, or we should be working in meters, so centimeters is x to the negative 2, so we'll just move the decimal place over. Then we've got 0.06 meters. Now, our formula for work is work equals the integral from a to b of f of x dx. Unfortunately, we're given an f of x, and we can assign our a value to be 0 and our b value to be the length that we want to pull this to. So we'll just plug all that in. Work is equal to the integral from 0 to 0.6 of 18x dx. And then if we get our antiderivative here, we've got 9x, get our parentheses in here, evaluated from 0 to 0.6. And then I am going to just use a calculator for this, but 9 times 0.06 minus 9 times 0, so basically minus nothing. So it's really 9 times 0.06, and that we are going to get 3.24. Now, actually it's not newtons, it's joules. Our work is measured in joules. Anyway, that's not just our answer. We have to actually put it in sentence form here. So the work done by stretching the spring, there we go. When I get to the bottom half of this, it seems like my pen doesn't really want to work. And then my spelling doesn't help. Anyway, stretching the spring, and I'm going to go back to the units that were given in the problem. I'm going to just say 60 centimeters, because that's what they asked, is 3.24 joules. And there you go. There's a work problem done. Not too difficult. And our last section is the average value of a function, 6.5. The temperature of a metal rod, 8 meters long, is T of x, which equals 7x in Celsius, at a distance of x meters from the end of the rod. This is a two-part question. What is the average temperature of the rod? And at what point on the rod is the temperature the average temperature of the rod? Okay, so for A, I'm just going to show you the formula here for average value, which is 1 over b minus a. The integral between a to b, why do we keep working offline? F of x dx. Sorry about that. Must be losing internet connection every once in a while. Anyway, so if we just plug in our values that are given to us, we have something that's 8 meters long, and we start at 0. So we'll just use this for our plug-in values. Here's our function, 7x, and this is going to be dx. So really, we just need to differentiate all of this. So we got 1/8 for the integral from 0 to 8, right? And actually, that's just going to, let me just do this, 7 over 2 x squared, and then that's going to be evaluated from 0 to 8. There we go. Then we plug in our 8. Obviously, we plug in 0, we're going to get 0, so we only need to do the 8. So that's going to be 1/8 times 7 over 2 times 8 squared. And I'm just going to do that in a calculator really quick because it's quicker. And this all works out to 28. Ooh, accidentally. Sorry about that. This all works out to be 28. 28. Yep, 28 degrees Celsius. So that's the answer for A. And B, they want to know when is it this average temperature. So we're just going to take the 28 and set it equal to this 7x the function and, you know, work it down, and then we're going to get 4 meters, which makes sense because, you know, the average would be like pretty much the middle. And if it's 8 meters long at 4 meters, that's where your middle point is. So anyway, we actually can't leave our answer this way. So I'm going to take these boxes off. We have to actually write a sentence that describes the answers for these. So the sentence for the first one would be the average temperature of the rod is 28 degrees Celsius. So temperature of the rod is 28 degrees Celsius. So that's the answer for A, written out correctly. And then for this one, it's going to be the average temperature occurs at a point 4 meters. So let's say the average temperature, let's say temp, occurs at a point of 4, at a point 4 meters from the end of the rod. So again, that just makes sense, right? The average of 2 points would be the middle of that point, or of those spaces. So anyway, there's the answer to that one. So that completes chapter 6. Just a few problems, one for each section except for 6.2, because 6.2 had 3 concepts in it. Again, I don't know why they didn't do cylindrical shells and they made a separate one for that one. But anyway, what do I know? I'm just a student. Maybe it's better for people to see it that way. Or learn it that way. But anyway, again, I'm a student, so if I made mistakes, just put them in the comments below. I'll answer you back. I'll give you a little kudos for catching me. And again, I do this just to help myself learn, and hopefully it helps you guys too. So see you in class, and see you for chapter 7.